5.5 is differentiation of the natural log of x. So in sections 5.1 and 5.2, you learned about, or you reviewed exponential and log functions. We skipped section 5.3. In 5.4, you learned about how to take derivatives of exponential functions, e to the x or e to the f of x. And in this section, we're going to revisit these log functions, but now talk about how to take derivatives of log functions. So this will be an absolute treat for you today. Let's go ahead and get started on these derivatives. Here are your rules. For x greater than 0, because remember, we can't take the log of a number that's 0 or less than 0. It's got to be a positive number. The derivative of the natural log of x is 1 over x. So this is a new derivative rule for you. You learned a new one last time with e to the x. This is your derivative rule for the natural log of x. Now, of course, most of the time that you see these, you're not going to see just the natural log of x. A lot of times it's going to be the natural log of some function of x. So when you see that, you're going to treat this in a similar way. Basically, you're taking 1 over whatever that function of x is and multiplying it by the derivative of the inside function using the chain rule. But a more simple way to write this is just f prime over f. So you're taking the derivative of the inside function and dividing it by the inside function. Now, what students find odd about these is that when you take derivatives for natural log functions, usually, not always, depending on what the function is, but usually your answer doesn't contain a log with them. It's going to go away when you take its derivative like this. So you're going to see what I mean in just a minute, but don't freak out, don't panic. If you started with a log and you took its derivative and you no longer have a log, that's okay. Let's go ahead and use these derivative rules to find some derivatives for log functions. The first one is going to be y equals e the negative 2 over x, so we're bringing back these exponential functions to review them, times the natural log of x. Now, this is going to need the product rule. It needs a product rule because we're multiplying two different functions of x together. So you can label them f and g if you'd like. And we'll go ahead and say that f prime is going to be the derivative of the inside function multiplied by the original function. So this will be just, the original times d dx of negative 2 over x. So we can find that right now too, but I feel like putting it in this notation first is helpful. So the derivative here of negative 2 over x is just taking the derivative of negative 2 times x to the negative first. So we'll find this separately. I know there's a lot of separate work we need to do here in order to find this derivative. So I would say that the derivative of negative 2x to the negative first, just rewriting this so that we can use the power rule, is going to be positive 2 x to the negative second. All right, so now we can rewrite this as e to the negative 2 over x times 2x to the negative second. If you'd like, you can go ahead and rewrite this with a positive exponent. And it's up to you what you decide to do with this exponential expression. If you want to keep it negative or if you want to keep it positive. I know it's kind of like we're picking and choosing what we're going to do here. But I'm just going to go ahead and say we'll leave this as e to the negative 2 over x times 2. Don't want to forget about 2 divided by x squared. And just kind of work with that. You can decide exactly how you want to rewrite it when that time comes. A lot just happened. And then for g prime is our new derivative. If g is the natural log of x, we just said the derivative of the natural log of x is 1 over x. So this is just ln x. It's not ln of some function of x. So its derivative is just 1 over x. So g prime is 1 over x. So now we can go ahead and put this derivative together using the product rule. So we're going to take f prime g plus fg prime. And I rewrote f in a few different ways, or I rewrote f prime in a few different ways, I should say. I'm going to hold on to this one for now, and if we decide to change it, then we can change it. So f prime, so it's 2 in the numerator, x squared in the denominator, and I guess we'll just keep the negative in the exponent for now in the numerator. So that's f prime times g. G is the natural log of x, plus f, and then times g prime. So those are all the components together. There's not a lot you can really do to simplify this, but you can factor out the e to the negative 2 over x if you want to do that. And you can factor out one of the x's in the denominator. So if you wanted to, you could rewrite this as e to the negative 2 over x, because they both have x's in the denominator. So we're going to take out one of them. And then what that would leave you with would be 2 over just 1 power of x, ln x. And then this whole thing would be gone, so you just multiply by 1. It makes it look a little bit better, but it's going to be kind of a messy derivative. So yeah, it's up to you. I think this looks better, looks a little more concise, but this is technically correct. There's really not a lot you can do here to simplify it. But it's done. Stick a fork in it, it's done. All right, next one. This one will be y equals the natural log of, and we're going to put a quotient in here, 2 over 3x. Now, if you're thinking, okay, fine, we're taking the natural log of a function of x, fine. Notice that to do that, we have this rule that says we would take f prime divided by f. Well, that means the derivative would be the derivative of 2 over 3x divided by 2 over 3x. It's kind of messy. We can do it that way, but we can also rewrite this so that the derivative is a little bit simpler. And the way that we would rewrite it would be using that quotient rule for logarithms. So this is a rule that was presented to you in section 5.2. So you could write this as the natural log of 2 minus the natural log of 3x. And that's going to be a little bit easier to work with. You could technically even split this up into the natural log of 3 plus the natural log of x. But I say let's just not get too crazy with our rewrite. But a lot of times rewriting using these rules for logarithms is really going to help you simplify the expression to make your derivative a lot easier. So usually we rewrite this first, just so that we don't have to deal with as much quotient rule if we don't have to. So we'll say that y prime is the derivative of the first term. Now remember, the natural log of a number is also a number. You can put this into your calculator, you'll get a number. It's a constant. The derivative of a constant is 0. Now we're going to use our new derivative rule to take the derivative of the natural log of 3x. We're going to take f prime over f. So if your inside function is f of x, you're going to take f prime, which is 3, and then you'll divide it by 3x, which is f. So now we can simplify your derivative by canceling out 3's, and what that leaves you with is negative 1 over x. Now, just so you can see that this would technically work both ways, we'll do it the other way without rewriting the function, and you can see how this would work. So alternatively, without rewriting, what you would be looking at is taking the derivative of the inside function divided by the original. So just using this rule as is without rewriting the function. So if we let f of x be 2 over 3x. Now, this is a case where you probably just rewrite this as 2/3 x to the negative first. You can do that. And then we'll talk about taking its derivative. So then f prime would be negative 2/3 x to the negative second. Then y prime would just be f prime over f. So negative 2/3 x to the negative second divided by positive 2/3 x to the negative first. Just using that derivative rule, f prime over f. And again, neither one of these derivatives have natural logs in them. It's okay. It happens. But if you're wondering, like, what, this does not look the same, well, that's where your exponent rules come in to simplify. Notice how much easier this was. This is the same derivative. It's just that we didn't rewrite the function first. So it just looks a lot crazier. But you can cancel between the 2/3, and that'll just leave you with a -1. And I'm going to move the x to the negative first to the numerator and x to the negative second to the denominator. And now you can see where this -1 over x comes from. So you get the same derivative. The moral of the story is it's just a lot easier to rewrite the expression first before you take the derivative. Let's do another one. All right, I have one example to fill the space. Oh, no, two examples, sorry. They're similar, but not the same. Okay, so let's see. Example 3 would be y equals the natural log of the square root of x squared minus 3. Now, this is another one that we can rewrite. Usually when we're taking derivatives, we rewrite radicals to rational exponents anyway. So the expression under the radical is what's being taken to the 1/2 power. Remember that you have a rule for logarithms that states that you can bring this power down in front of the logarithm. That rule was taught to you in college algebra, but also in section 5.2. It's that power rule for exponents. So this is a totally valid move here, that power is being applied to the expression inside the logarithm, but you can move it in front and now it's a constant multiple. Rewriting this expression is going to make your life a lot easier. If you're trying to take the derivative by taking f prime over f, you don't want to have to deal with this. This is a mess with the chain rule. You can do it. I just would prefer to not if I were you. Always rewrite the function to simplify it before you take the derivative. Okay, so now this is my expression. I've got a constant multiple in front of it. That's fine. So when I take y prime, I'm looking at the natural log of some function of x. The derivative is just going to be that constant multiple of 1/2 times f prime over x, or f prime over f, not x, times f prime of x over f of x. So this is straight from that definition I gave you on the first page. So f prime is 2x, and f is x squared minus 3. Now the 2's will cancel. And what this leaves you with is x over x squared minus 3. That's your derivative. You would get the same derivative if you went through this process, but it would be pretty messy. There'd be a lot of simplifying radicals to do, probably some complex fractions to work with. Rewrite the function first. Number 4, now this one's similar, and there's a reason that you're being given this example now. This one is the square root of the natural log of x squared minus 3. Notice how similar these two look, but not the same. In this example, the square root is being applied to the natural log. In the first example, example 3, the square root is not being applied to the natural log, it's being applied to the quantity inside the natural log. That's a big difference. We can still rewrite this by taking it to the 1/2 power, but now the natural log itself is being taken to the 1/2 power. Now, you cannot use the power rule here. This is a big no. I don't know where my red pen is, where I like yell about things and say no. You cannot use the power rule like this. This was told to you in 5.2. I remember writing a separate note about it, and then the separate note appeared again on another page. It was the natural log of, like, I don't know what the exponents were, a to the p. It's p ln a, but it's not the same as ln a to the p. Okay, so these two are good, not this one. Okay, if you're taking the whole logarithm to a power, it's not the same thing. So we're going to have to use the chain rule here, no big deal. We're going to find the derivative. It's just going to be a little work because we really can't find a way to rewrite this function. But let's go ahead and use the chain rule. Use chain rule. I'm going to bring the 1/2 out front. I'm going to rewrite the inside function. I'm going to decrease the power by 1. Whoops, that's supposed to be a -1/2, and I don't know why it looks so funky. And then I'm going to multiply by the derivative of the inside function. The derivative of the inside function is going to be, if your inside function is f of x, it's going to be f prime over f. I'm going to take f prime, which is 2x, and divide it by f. Okay, so this is f prime over f. Okay, and then simplify if you can, but there's really not a whole lot you can do here. What you can do, though, is you can cancel out these 2's. They're just being multiplied together, the 1/2 and the 2. So that's something. I'm going to move this entire log down into the denominator. I mean, everything else is just going to kind of stay where it is. So this x in the numerator stays. And then I still have this factor of x squared minus 3. And then in the denominator, I'll just the natural log of x squared minus 3 under the radical. And that's it. That's all we can do to this one. We'll put a box around it. All right. Now we're going to find an equation for the tangent line. So back to doing some of these applications from earlier chapters, but using logarithmic derivatives with them. Find the equation of the tangent line to f of x equals the natural log of x squared at the point or at x equals 1. Now, since you know that you need a point and a slope, you weren't actually given a point here. So you need to find a y value for this point. You might want to just do that now. So let's say we need a point and a slope. To find the point, we'll find f of 1. And that'll give us the y value. And it's the natural log of 1 squared. The natural log of 1 is 0. That's something that was taught to you in section 5.2. You can also put that into your calculator. So now you can say that your point is 1, 0. Okay, so that's that. We have that so that later when we're ready to go and put our point slope formula together, we've got the point. Let's focus now on finding the slope. To get the slope, we need f prime. In order to do that, we're going to rewrite f of x. You can leave it like this if you'd like. It's not that big of a deal. It's not super complicated. I'd just rewrite it if it were me, using that power rule for logarithms. So I'm going to rewrite f of x as twice the natural log of x. So this was just a rewrite. And then we'll take f prime. The derivative of the natural log of x is 1 over x. So you've got now 2 over x. Once you get your derivative, evaluate it at this x coordinate to get the slope. F prime of 1 is 2 over 1, which is 2. This is your slope. Now you have a point and a slope, and that's all you need to write the equation for your line. So let's go ahead and do that. Y minus y sub 1 is m times x minus x sub 1. So y equals 2x minus 2. And since we have not yet done this for a natural log function, let's go ahead and look at this and make sure it makes sense on the graph. Our original function is the natural log. I'd always put in the original in case you rewrite it wrong. Remember, for your natural log function, it's just the ln button right here. So it's the natural log of x squared. I already know I'm in Zoom 6. I'm going to keep it that way. The equation for the tangent line is 2x minus 2. I'm looking for this to go through the point 1, 0. All right, so there's the natural log function. And it's going through the point 1, 0 with my slope being 2, and it's going through that point on the curve. It is definitely tangent at that point. That's what it looks like. I wonder if some of you were thinking like, wait, I thought she said the natural log could only be positive. I said the input for the natural log can only be positive. It can only be evaluated for positive numbers. But in this case, because it's squared, you're getting values, squaring the values. So technically, you can evaluate this at negative values of x because it's getting, because it's getting squared. And then you're evaluating the log at that number. So that's why it works this way. Okay. Next, we are going to find where our logarithmic function is increasing, decreasing, concave up, concave down, etc., etc. This is going to be f of x is the quantity natural log of x squared. Now, you know that I'm going to make this note right now. You know it. The natural log of x, quantity squared, does not equal twice the natural log of x. The power rule does not work here because the entire log is being taken to the power. If it was just x being taken to the power, that would be okay, but it's not. So you cannot rewrite it. We might also want to discuss the domain here. Remember that we cannot evaluate a natural log for values of x that are 0 or less than 0. So we might want to go ahead and note the domain from 0 to infinity. And if you're wondering, like, well, technically it's being squared, it doesn't matter because it's not getting squared until after you evaluate the natural log. You cannot evaluate the natural log for values of x that are 0 or less than 0. So even though it's being squared, you still have a domain from 0 to infinity, not including 0. So that's important to note. If I'm looking for intervals where it's increasing, decreasing, concave up, concave down, I need a first derivative and I need a second derivative. And I need to write really small because I got to fit all of this in this space. So I'm going to take f prime of x. I'm going to bring my exponent down, use the chain rule. Chain rule. Twice ln x to the first power multiply by the derivative of the inside function. The derivative of ln x is 1 over x. So f prime is 2 ln x over x. Now, if I'm looking for critical numbers, I need to find where f prime is 0 or where f prime does not exist. One thing we might want to note right away that f prime of x does not exist when x equals 0, because x equals 0 makes the denominator 0. However, 0 is not in the domain. It's really important, especially with logarithmic functions, to write our domain first, just like we did when we had radical functions in the previous chapter. Not in domain. We're not going to use that value. It doesn't mean anything to us. Nothing can be happening there because we can't evaluate the function there. The other thing we're going to do is look for places where f prime of x equals 0. And that's where twice the natural log of x equals 0. So in order to do this, we're going to go ahead and say divide both sides by 2. We'll say, all right, ln x equals 0. And this is not the same situation that we had with the exponential function. With the exponential function, we said, yeah, it can't be equal to 0. But that's not the case here. If I wanted to isolate this x, I could undo the natural log by making e the base on both sides. We did this in 5.2. I'm almost positive. If we did not, you at least learned the property that e to the ln x was x. So now you can say that x is e to the 0. And e to the 0, well, the real number to the 0 power, which is 1. And this is going to be a critical number. So that's your critical number. You found it. And we'll go ahead and use sign analysis with your critical number to determine intervals on which the function is increasing or decreasing. Your critical number is in the domain, so that's really important. We're not going to test any values that are not in the domain, so make sure we understand that. Basically, you're just going to have the critical number at 1. The lowest value we can obtain is 0, and it goes all the way up to infinity. So when you're testing this, you're testing the first derivative. Don't pick 0. First of all, if you test the first derivative at 0, you're going to get a big error. But also, 0 is not in the domain. So you're going to have to test something like 1/2 or 1/3 or something between 0 and 1. So I'll test 1/2 and then 2. Okay. We're going to get the signs here. I've got a different function there right now. So let me put in my expression, the derivative 2 ln x over x, 2 times natural log of x divided by x. Don't forget to close parenthesis there. And I'll go to my table. I'll pop in 1/2 and use this value for 2 to the 30 here. So at 1/2, it's a negative derivative, and at 2, it's a positive derivative. So I can say that if the derivative is negative, my function is decreasing. If it's positive, the function's increasing. So we can go ahead and make a conclusion right here. I actually have 2 conclusions because we should also say something about the relative extrema. We can't just act like we're going to ignore the relative extrema. At 1, we have a local minimum or a relative min. At 1, f of 1. But that's okay because we know f of 1, the natural log of 1 is 0. We should know that. Let's get used to it. And then 0 squared is still 0. So we have this relative min at 1, 0. No, you're just like, you didn't ask me for that. That's fine. I'm telling you, include it. We need to talk about it. So we can go ahead and say that f is decreasing. I'm going to write small because I still need to talk about my second derivative. Decreasing from 0 to 1. I'm increasing on 1 to infinity. And we have a relative min at 1, 0. I mean, it's on here, so I might as well just, I want to write it again so it's clear. Okay, all of that popped out of our first derivative test. Okay. Now let's look at the second derivative and we'll talk about concavity. So we'll do that next. F double prime. So we're going to go back to our first derivative, and we got a couple different things we could do. I'm just going to go ahead and use the quotient rule. So we'll do f prime g minus f g prime. The derivative in the numerator is 1 over x multiplied by 2. So in the numerator, we have f prime, which is 2 over x, times g minus f, which is the numerator, times g prime. G prime is 1, all divided by g squared. Okay, so the derivative in the numerator is 2 over x, so f prime g minus f g prime all over g squared. We'll simplify. The nice thing about this is even if you were like, I'm going to have a complex fraction, those two x's are going to cancel. And now we just have 2 minus 2 ln x over x squared. Now, again, the second derivative is never going to not exist because we can't have a value of x equals 0. So we're going to go ahead and say f double prime of x does not exist, never, because 0 is not in the domain. 0 is not inside 0 to infinity. And we do need to look, though, at when we have f double prime of x being equal to 0 to get a possible point of inflection. And that's going to happen when 2 minus 2 ln x equals 0. That means 2 ln x equals 2, ln x equals 1. And you're trying to figure out, well, ln of what number is 1? Well, if you're not sure, if you're trying to isolate the x, you can, again, just make e the base on both sides. And then you'll get x equals e. Oh, my important conclusion in my paper slipped. Terrible. X equals e. This is a possible point of inflection. It will fit. Oh my gosh, my paper slipped. You guys couldn't even see it. Sorry. X equals e, possible point of inflection. Definitely a place where we might have our concavity changing. So let's go ahead and do a sign analysis and see what happens at E, but that's going to be our only possible point of inflection if we see that concavity change. And again, I'm only going to look at this from 0, only from 0 to infinity. But E is the critical number, and I'm looking at values that are between 0 and E. E, remember, is 2.7 something, so you can always test 1. And then maybe 3. If you don't remember E, just pop it into your calculator, e to the first, and you'll get that decimal approximation. Okay. I'm going to go ahead now, and I'm going to put the second derivative into my graphing calculator. So we have in the numerator 2 minus twice the natural log of x. Don't forget your second parenthesis, divided by x squared. And then we'll look at our table. I'm looking at 1, which is already in here. Then I'll put a 3 in here. So at 1, we have 2, so it's greater than 0. And at 3, it's negative 0.022, so less than 0. So we are going to be concave up, concave down, and we're going to check this too when we're done to make sure that this matches up with our graph. That means that E is an actual point of inflection. So let's make our conclusion, and then we'll find that value. So we'll say concave up on 0 to E, concave down from E to infinity. and then we have a point of inflection at E, f of E. Well, f of E is just going to be ln E squared. Ln of E is 1. Square it and you still get 1. Okay. Let us put this into our graphing calculator and make sure that the function is doing what we think it's doing, what our data shows it's doing. I'm going to put in the original. The original is ln x quantity squared. So ln x, 2 parentheses, square it. The whole thing is getting squared, not just the x. Be really careful there. I know I keep saying it, but because it's a place where things end getting messed up. We'll graph the function. We'll see what's happening. Now, it's kind of hard to see what's happening with points of inflection. Really, I didn't need to include this left-hand side of the graph. But let's see. We had it decreasing from 0 to 1. That's happening. Increasing from 1 to infinity with relative minimum at 1, 0. Yep, check. And then we had it concave down from 0 to E. Now, that's a little bit harder to check. Concave down frown. See, now I just don't know. Concave. Oh, no. Concave up from 0 to E. I know. Why did I say concave down? I'm like, that doesn't look like what's happening on the graph. Okay. Concave up from 0 to E. And then E is, remember, like 2.7 something. So if you think about 1, 2, 3, we're concave up until about right here. Concave up, concave down, frown. So you can see it's hard to see an inflection point at E, but it's occurring at E1, which is about right here that the concavity changes. So it goes from concave up to concave down. But you'll see it's a kind of shallow the way that concavity works, but it's definitely concave down. So that's pretty cool. Okay, the last thing we're going to do in this section, I know, are you bummed out that I don't have an implicit differentiation problem for you? Oh, I'm like a total failure now. Let's see, do I have one somewhere in here that I could throw at you? No, you'll see one on the homework. Don't worry. But I don't know. All right, that's fine. We'll talk about it. Maybe in the next section, I'll throw one in at the end. I don't have one ready right now. What happened? Logarithmic differentiation. We're going to talk about how to take derivatives of functions using logarithms where maybe they did already have logarithms in them. And maybe to you that seems like, why the heck would I want to introduce a log when there isn't already a log? Well, you've seen already that when you have a logarithm, we can apply that power rule for logarithms to simplify. So sometimes when you have a really complicated derivative to take, it's actually easier to take a logarithm and simplify the derivative by using some of those properties for logarithms. So we're going to talk about something called logarithmic differentiation. We're going to take the natural log of both sides. And if you're wondering, like, both sides, well, we're going to have like a y equals. So we're going to take the natural log of both sides and use properties of logs to expand our expression. Then we'll take derivatives of both sides. So that means we'll need to do an implicit derivative on the left. We'll solve for dy dx and replace y with the original. So again, logarithmic differentiation can make differentiating some functions easier, as well as give us a technique to apply to some functions we couldn't otherwise differentiate. I think it should say couldn't otherwise differentiate. I'm going to remind you of these rules. We've used them a couple of times today. The natural log of a times b is the natural log of a plus the natural log of b. The other one I had up here somewhere, but it was like ln a to the p is p ln a. There's one more rule for quotients. I don't know if we're going to use it here, but it just says that you can subtract those two logarithms. So these are all from 5.2. All right, so here's the function. And if you're kind of like, no, I'm never going to use this, well, I'm going to ask you to do it on your exam. And also, when I give you this function, you change your mind. It is 3x minus 2 quantity squared times x squared minus 1 to the 5th power. Oh, I hear some of us changing our tune right now about logarithmic differentiation. Times 8x minus 3 cubed. So this is horrible. And imagine if I would have given you something like this in chapter 3. You'd be like, oh, it's like product rule twice with the chain rule. It's an absolute mess. Or you could expand the whole thing out, which is even messier, even though it doesn't even use calculus to expand it out at least. So what we're going to do is we're going to use logarithmic differentiation to simplify. And what we're going to do is first take the natural log on both sides. We're going to make there be a log. As long as I do the same thing on both sides, it's valid. Now, I'm going to use this rule right now because I'm basically just going to be applying the log on both sides. But, well, I'll just write it twice. 3x minus 2 squared. X squared minus 1 to the 5th. 8x minus 3 cubed. But what I can do now is I can write that, because I have the log of a product, as the sum of 3 logarithms. So I'm taking the log of a product, I'm just going to split it up into the sum of 3 logs. So this is going to be the natural log of 3x minus 2 squared plus the natural log of x squared minus 1 to the 5th plus the natural log of 8x minus 3 cubed. Okay, now don't forget, on the left-hand side, you still have the natural log of y. Okay, so we're using the log properties to expand. We're actually not done yet. We have a little more expanding to do. Rewrite the left-hand side. And now we're working here. We're going to expand by now using this power rule that allows us to take the exponent and bring it out front. So this is twice the natural log of 3x minus 2 plus 5 times the natural log of x squared minus 1 plus 3 times the log of 8x minus 3. Once you have this whole thing expanded using the properties of logarithms, then you'll differentiate using the rules for derivatives. Remember that the derivative of the natural log of f of x is f prime over f. So this is an f function. That's an f function, and this is an f function. All right, so let's go ahead and take some derivatives. Don't forget to take your derivative on the left-hand side. I'm wagging my finger at you, sorry. The derivative on the left-hand side, oh, I'm getting ahead of myself, is 1 over y dy dx, because the derivative of the ln of x is 1 over x. The derivative of ln of y is 1 over y. Don't forget to chain on the derivative of the inside function. This is technically an implicit derivative. All right, now we'll take some more derivatives. 2 times the derivative of the inside divided by the original. Let me do that again. The derivative of the inside divided by the original, and 3 times the derivative of the inside divided by the original. We'll simplify it a little bit. There's not like a whole ton we can do here. So this says 1 over y dy dx is 6 over 3x minus 2 plus 10x over x squared minus 1 plus 24 over 8x minus 3. Okay, just multiply the numerators. Now, we're looking for dy dx. It says solve for dy dx. In order to solve for dy dx, we need to just multiply both sides by y. multiply both sides by y to solve for dy dx. Okay, so I want to have just the derivative of y with respect to x. In order to do that, I'll multiply both sides by y. Y over y gives me 1. Okay, I'll slightly switch colors here. dy dx. All right, so dy dx equals, I'm going to take this whole expression. You're going to really like this, by the way, when I get done with it, because you're going to be like, wait, I don't have to do anything else? For 8x minus 3. And multiply it by y. And if you're like, what do you mean multiply by y? I don't mean just y, because then you'd have an expression in y and x, and I don't want that. I want d dx. So I'm going to take my y and sub it out with this original. So when I say multiply both sides by y, I mean this thing. 3x minus 2 quantity squared times x minus 1, or x squared minus 1 to the 5th, times 8x minus 3 cubed. This is y. You're not going to believe this. I'm putting a box around it. That's the derivative. I know it looks terrible, but you know what? That's actually kind of the cool thing about doing these is you don't have to do a ton of simplifying. Just do what you can and leave it. That's it. Now, another place where this is going to come in handy for you is going to be if you have a variable in the base and in the exponent. I have one last example for you here. That would be something like y equals x to the 3 minus x. All right, so a variable in the base and in the exponent, we don't have a rule for this. We do not have a rule for this. So this would be like f of x to the f of x power. We don't have it. Or even like y equals x to the f of x. We don't have it. You could even say this is g of x. Maybe I should have called that something else. But we don't have a rule for an expression of x to an expression of x. So this is why we have to use logarithmic differentiation. There is no other way we could do this without logarithmic. In the last example, like, yeah, we could have used a lot of product and chain rules to do it. But in this example, we don't have a rule. There's no other way we can do this. We have to use logarithmic differentiation. All right, so in order to use logarithmic differentiation, I am going to take the log on both sides. ln y is ln x to 3 minus x. Once you take the log on both sides, now you can just willy-nilly pull that power out front using the power rule. Don't forget your parentheses. If you lose your parentheses, then it's just going to look like 3 minus the quantity x ln x, which is not what you want. That whole exponent's getting multiplied by the logarithm. Okay, now this is all ready to go for us to take the derivative. You can, if you would like, you can multiply the 3 minus x to the ln x, but it's not going to matter because regardless, this still needs the product rule. You are taking a function of x and multiplying it by another function of x. So we use the product rule on the right-hand side. On the left, I'm taking the derivative in this step, and I did not take the derivative. On the left, we're going to take the derivative with respect to x. So this is going to be 1 over y dy dx. The derivative of the natural log of y is 1 over y. When we take a derivative of y with respect to x, we have to chain that on. Equals. And then we're going to use the product rule. We can let our factors be f and g. F prime is -1 times g plus f times g prime. Derivative of the natural log of x is 1 over x. And again, don't freak out because you took this derivative and the ln went away. That happens. I know I keep repeating it, but it's because students keep feeling like, wait, my natural log is gone. I did something wrong. That's not the case. Okay, there's, again, not a ton that you can even do with this expression. We can simplify it a little bit, and then we'll just multiply both sides by y. So I'm just going to rewrite the left for now. On the right, there's not a ton we can do. Plus 3 minus x over x. Multiply both sides by y. And when you do that, you get dy dx equals negative ln x plus 3 minus x over x multiplied by y. So the expression for y was x to the 3 minus x. All right, now, I'll tell you what not to do. Here's what you can't do. Do not take this expression and cancel out the x's. So maybe if you were thinking like, oh, maybe I'll distribute this, that's fine. You can distribute it. Don't do that. You can't do that. This is not just x, it's x to a power. So if you were thinking like, maybe I'll cancel these out, you can't. It's not x, it's x 3 minus x. They're not the same. Don't do that. If anything, I would say leave it. It's done. Some of these just aren't going to look that great, and that's okay. This is done. Also known as stick a fork in it. Okay, so I know I said I didn't have implicit differentiation for you, but technically this was implicit. Should I add one on here real quick? Oh, I got to pick my daughter from preschool in 5 minutes. What can I do in 5 minutes? I have to leave in 5 minutes. Okay, let me give you a real quick example. Implicit. We'll say that it's ln of xy equals, we'll be quick, x plus, oh gosh, I don't know. She needs to decide y squared. Okay. Got it. All right, we're going to differentiate implicitly. Ready? I'm adding an example. Here we go. The derivative on the left is the derivative of the inside function divided by the inside function itself. This uses the product rule. We've already said that the derivative of x times y with respect to x is f prime g plus f g prime. Okay. So the derivative of the inside function is y plus x dy dx divided by the original, which is x y equals 1 plus 2y dy dx. Okay, now we need all the dy dx's on one side and everything else comes to the other side. It's kind of up to you how you do that. I'm going to split up this fraction using the common denominator. So I'm going to say this is y. I'm going to hook my y so they don't get mixed up with my x's. Y over xy plus x over xy dy dx is 1 plus 2y dy dx. Ooh, I have to kind of think this is a good problem. Can't believe I thought of this on the fly. And then I want to have all the dy dx's together. Now, if I would like to, I can cancel out these common factors in the numerator and denominator. I'm going to leave my dy dx's on the left. So I'm going to say I have 1 over y dy dx minus 2y dy dx is 1 minus, and then this term will be 1 over x. I'll move it to the other side. Change the side, change the sign. All right, so we're good to go there. Go ahead and factor out your dy dx. That leaves you with 1 over y minus 2y is 1 minus 1 over x. This is going to be a complex fraction, by the way. I'm going to pull it up here. We'll look at it over here. Divide both sides by this factor of dy dx. So 1 over y minus 2y. And then multiply every term by the LCD. The LCD is x, y, the two denominators that you see. Times xy, times xy, times xy, times xy. And then when we simplify this, we have dy dx equals xy minus the x's cancel and you just get y, divided by the y's cancel and you just get x minus 2x y squared. You're done. And I have just enough time to hop in my car and go to preschool pickup. Awesome. Hopefully this will be helpful. You'll see a little bit of this on your homework, not a ton, but so it'll be logarithmic differentiation, a little bit of implicit. You'll see some work with increasing, decreasing, relative extrema, concave up, concave down, possible points of inflection. In addition to, I'm working backwards here, all the derivatives of logarithmic functions and using those derivative rules, knowing when to rewrite the function and when you can't rewrite the function. So just using everything you've learned today in conjunction with 5.2 to do an awesome job in your exponential and log function derivatives in the chapter. But anyway, enjoy. I hope you will enjoy as you learn, and enjoy the rest of your day as well. And I'll see you later.